In this video, we are going to learn about collagen. So, for an introduction, collagen comprises a family of fibrous glycoproteins that are present only in extracellular matrix. Collagens are found throughout the animal kingdom and are noted for their high tensile strength, that is, their resistance to pulling forces. It is estimated that a collagen fiber 1 mm in diameter is capable of suspending a weight of 10 kg without breaking. That means collagen of 1 millimeter diameter fiber is capable of suspending a weight of 10 kg. Collagen is the single most abundant protein in the human body, consisting of more than 25% of all protein, a fact that reflects the widespread occurrence of extracellular materials. Collagen is produced primarily by fibroblasts, the cells found in various types of connective tissue, but also by smooth muscle cells and epithelial cells. Collagen is produced primarily by fibroblasts, the cells found in various types of connective tissue, but also by smooth muscle cells and epithelial cells. To date, 27 distinct types of human collagen have been identified. Each collagen type is restricted to particular locations within the body. But two or more different types are often present together in the same extracellular matrix. Additional functional complexity is provided by mixing several collagen types within the same fiber. These heterotypic fibers are the biological equivalent of metal alloys. It is likely that different structural and mechanical properties result from different mixtures of collagens and fibers. Although there are many differences among the members of the collagen family, all share at least two important structural features. One, all collagen molecules are trimers consisting of three polypeptide chains called alpha chains. Along at least a pair of their length, the three polypeptide chains of a collagen molecule are wound around each other to form a unique rod-like triple helix. The alpha chains of collagen molecule contain large amount of proline, and many of the proline and lysine residues are hydroxylated following synthesis of the polypeptide. The hydroxylated amino acids are important in maintaining the stability of the triple helix by forming hydrogen bonds between component chains. Failure to hydroxylate collagen. The alpha chains of collagen molecule contain large amount of proline. Many of the proline and lysine residues are hydroxylated following synthesis of the polypeptide. The hydroxylated amino acids are important in maintaining the stability of the triple helix by forming hydrogen bonds between component chains. Failure to hydroxylate collagen chains has serious consequences for the structure and function of connective tissue. This is evident from the symptoms of scurvy, a disease that results from a deficiency of vitamin C, that is ascorbic acid, and is characterized by inflamed gums and tooth loss, poor wound healing, brittle bones, and the weakening of the lining of blood vessels, causing internal bleeding. Ascorbic acid is required as a coenzyme by the enzyme that add hydroxyl groups to the lysine and proline amino acids of collagen. A number of the collagens, including type 1, 2, and 3, are described as fibrillar collagen because they assemble into rigid cable-like fibrils, which in turn become packaged into thicker fibers that are typically large enough to be seen in the light microscope. The side-by-side packaging of the rows of collagen 1 molecule within a collagen fibril is depicted in the figure. The fibrils are strengthened by covalent cross-links between lysine and hydrolysine residues on adjacent sites. One figure depicts several levels of organization of a fibrillar collagen. The collagen molecule or monomer is a triple helix consisting of three helical alpha chains. Some types of collagen contain three identical alpha chains and thus are homotrimers, while others are heterotrimers containing 2 or 3 different chains. Each collagen 1 molecule is 295 nm in length. Collagen 1 molecule become aligned in rows in which the molecules in one row are staggered relative to those in the neighboring row. A bundle of collagen 1 molecule, such as that shown here, forms a collagen fibril. The staggered arrangement of the molecules produces bands, horizontal black lines in the illustration, across the fibril that repeat with a periodicity of 67 nm. It is equal to the length of the gap between molecules plus the overlap. An electron micrograph of human collagen fibril observed after metal shadowing. The banding pattern of the fibril is evident. An atomic force micrograph showing the surface of the collagen fibril that suggests that its subcomponents are twisted spirally around the fibril axis like a rope. The banding pattern remains evident. The arrows point to places where the fibril is highly unwound, as would occur if you were to twist a rope in the opposite direction. It is wounded. So an overview of the macromolecular organization of the extracellular matrix. The proteins and polysaccharides shown in this illustration will be discussed in the following sections. The proteins depicted, such as fibronectin, collagen, and laminin, contain building sites for one another, as well as binding sites for receptors or integrins that are located at the cell surface. The proteoglycans are huge protein polysaccharide complexes that occupy much of the volume of the extracellular space. So collagen, now we have already learned. Fibronectin is another one. Integrin is also there, along with the laminin and proteoglycan. Never forget the structure of all these molecules. Please Google and learn them. This cross-linking process continues through life and may contribute to the decreased elasticity of skin and increased brittleness of bones among the elderly. Recent studies that probe the surface of collagen fibers suggest that they are composed of strands that are twisted around the axils of fibril to form a structure that is more like a nano-sized rope than a cable. Among the various components of the extracellular matrix, collagen molecule provide the insoluble framework that determines many of the mechanical properties of the matrix. In fact, the properties of a particular tissue can often be correlated with the three-dimensional organization of its collagen molecule. For example, tendons, which connect muscles to bones, must resist tremendous pulling forces during times of muscular contraction. Among the various components of the ECM, collagen molecules provide the insoluble framework that determines many of the mechanical properties of the matrix. In fact, the properties of a particular tissue can often be correlated with the three-dimensional organization of its collagen molecule. For example, tendons, which connect muscles to bones, must resist tremendous pulling forces during times of muscular contraction. Tendons contain an extracellular matrix in which the collagen fibrils are aligned parallel to the long axis of the tendon. And thus parallel to the direction of the pulling forces. The cornea is also a remarkable tissue. It must serve as a durable protective layer at the surface of the eyeball, but must also be transparent so that light can pass through the lens to the retina. The thick middle layer of the cornea is the stroma, which contains relatively short collagen fibrils that are organized into distinct layers. The layered structure of stroma is similar to that of plywood. The fibrils of each layer are parallel to each fibril in the layer but nearly perpendicular to the fibrils in the layer on either side. This plywood-like structure provides strength to this delicate tissue, while the uniformity of size and ordered packing of the fibrils minimize the scattering of incoming light rays, thereby promoting the tissue's transparency. So, which are the various sites? Tendon, and along with that, the middle layer of cornea, the stroma, and the eyeball, like that structures. Given the abundance and widespread distribution, it is not surprising that abnormalities in fibrillar collagen formation can lead to serious disorders. Burns or traumatic injuries to internal organs can lead to an accumulation of scar tissue, which consists largely of fibrillar collagen. A common condition described as fibrosis results from excessive production of collagen containing connective tissue. Fibrosis occurs most often in the lungs, pulmonary fibrosis, and liver cirrhosis, where the collagen containing scar tissue gradually replaces the normal tissue of the organ. Mutations in genes encoding type 1 collagen can produce osteogenesis imperfecta, a potential lethal condition characterized by extremely fragile bones, thin skin, and weak tendons. Osteogenesis imperfecta. Mutations in genes encoding type 2 collagen alter the properties of cartilage tissue, causing dwarfism and skeletal deformities. Mutations in the number of other collagen genes can lead to a variety of distinct but relatively related defects in collagen matrix structure called Ehlers-Danlos syndrome. Persons with one of the syndromes have hyperflexible joints and highly sensitive and extensible skin. So, which are the diseases associated with the collagen synthesis? Fibrosis, mainly pulmonary fibrosis and liver cirrhosis, where the collagen containing scar tissue gradually replaces the normal tissue of the organ. Mutations in genes encoding type 1 collagen can produce osteogenesis imperfecta, a potential lethal condition characterized by extremely fragile bones, thin skin, and weak tendons. Mutations in genes encoding type 2 collagen alter the properties of cartilage tissue, causing dwarfism and skeletal deformities. Mutations in the number of other collagen genes can lead to a variety of distinct but related defects in collagen matrix structures called Ehlers-Danlos syndrome. Persons with one of the syndromes have hyperflexible joints and highly extensible skin. Not all collagen form fibrils. One of the non-fibrillar collagens is type 4, whose distribution is restricted to basement membrane. Basement membranes are thin supportive sheets, and the type 4 collagen molecules are organized into a network that provides mechanical support and serves as a lattice for the deposition of other extracellular materials. Unlike type 1 collagen, which consists of long uninterrupted triple helix, the type 4 collagen trimer contains non-helical segments interspaced along the molecule and globular domains at each end. The non-helical segments make the molecule flexible, while the globular ends serve as a site for the interaction between molecules that give the complex its lattice-like character. Mutations in type 4 collagen genes have been identified in proteins with Alport syndrome, an inherited kidney disease in which the glomerular basement membrane is disrupted. So that is what Alport syndrome. Alport syndrome is something which is related with the collagen deformity or collagen malfunctioning in the basement membrane, which causes a inherited kidney disease because it creates problems in the glomerular basement membrane, which will be, influencing the filtration of blood. So that causes a inherited kidney disease. So that is what is meant by Alport syndrome. Alport syndrome. Never forget Alport syndrome.